let's start, and then you know, the rest will come in as they can. We're now going into a new phase, the last model that we're going to deal with, and it's going to be the von der Marlsberg model, which deals with the problem, or at least the phenomenon, of self-organization. Okay, this is going to be sort of a different field compared to the other two models, the Hopfield and the backpropagation multi-layer perceptron that we've been dealing with previously. It's essentially, the key difference is that in the previous models, we were kind of introducing the concept of architecture, activation function, and like learning rules and things like that. Okay, so like we're learning these key functions or processes that in general you see in a lot of the large language models nowadays. Okay, but now we assume that you've learned that. Okay, you are kind of established and solid in your understanding that, well, any basic neural network will have the architecture, the activation function that has to be nonlinear, and it has a learning rule, and that these three basic parts, you combine them in fancy ways and all that, you get all sorts of neural network models. And up to this point, we didn't really care about the nature of the stimuli itself, because we always use binary coding. So up to this point, in this course, we've always used somewhat arbitrary, arbitrary binary tokens. Right? We've always kind of like translated our real life stimuli or psychological behavior or outputs, into some sort of a binary state. We never really cared about the nature of these binary states. We only assumed that, well, they just means, different features in the environment or different kind of thoughts or actions that we do. Okay? So it's arbitrary in that sense, in that the mapping or the real connection that we did was something that we just assumed in order to solve a so-called a deeper problem. Okay? However, one could argue that nature or physics does not appear arbitrary. Does it? Does anyone think that your experiences are arbitrary? You would not use that word, at least, in the first description, right? Maybe some philosophers eventually will say, no, yes, everything is arbitrary. Okay, but you have to think a lot and all that before you get there. Right at the outset, when you are a baby, certainly, your system does not think that its sensory experiences or its actions, it would not, arguably, even if a baby can express the sense of arbitrariness, at least it functions in a way that its system does not assume arbitrariness, right? It actually assumes there is some cause. Rather, it is causal. Even if we don't know or don't understand the cause, we do come from an assumption that there is a cause. Okay? All right, so this setup is kind of like to introduce to you the idea of self-organization, because you have to understand the problem first, like where it comes from, and then the neural phenomena of self-organization makes better sense, okay? So it has to start from this kind of beginning of a first principles, is that the environment, as it were, is not arbitrary. our experience actually, our psychological experience is that it is not arbitrary, at least at the first instance of it, okay? And rather we assume that there is some cause, and then it begs the question, okay, what is this cause, right? That is the burning question in our brains. Why, did this happen? Why not something else? How do we explain this? It seems to be like if you do not know or understand something, we don't feel very comfortable with ourselves. That is kind of a very biological living experience, isn't it, right? Okay, I've not met anyone who is just comfortable with not understanding anything, right? Okay, so it seems to be that our system is always trying to form some sort of causal model, okay? And there's this drive, right, that is kind of shaping our neural networks. So this is, immediately you can appreciate that, and as we talk about this more, there seems to be something mysterious in the way our neural networks function, okay, that is different from the backprop and the hot field in a sense that in the backprop and the hot field, we have a much clearer, we have a sort of a clearer kind of definition of, yes, it makes sense that learning has to be about comparing between, different, a particular output and a desired output. It makes very concrete sense, okay? Hot field, it makes sense that, yeah, the memory should be about, like, I can retrieve something based on partial features if I just encode itself or something like that, okay? But here, when we try to pinpoint what is it that this causal drive, this drive to find a cause and all that, what is it? It's actually very, very hard to define. So so we have this motivation. So our neural system system's psychology, okay? You talk about that, like it's a biological system, biophysical system that instantiates a psychological phenomena, okay? Our neural system's psychology is motivated to answer this, it seems, okay? But this is very difficult to define, this operation. At least from our objective point of view. Can't get an objective function. So we hit some sort of a wall here, where our understanding of how neurons, the architecture connects, at least from the base principles of it, that, okay, if I have active units and they have weights connecting to each other, I can explain phenomena X, phenomena Y. Oh, if I have an activation function or a learning rule, I can explain how this neural network encodes things and retrieves things. But this notion of trying to explain a cause or trying to have this, or having this motivation to get at a cause, we really do hit at a wall here. Even in LLMs nowadays, right, you find that, well, I would argue the LLMs don't really have any motivation to do anything. We're just squeezing errors and data into it, and then it gives us some output. It doesn't doesn't seem to, or at least the value or the way we want to understand the LLM doesn't seem to sort of care about how it instantiates, whether it has displayed this phenomena of having some sort of a drive or a behavior that is trying to understand some cause. That there's no, this kind of wall. We don't really care so much about it in LLMs. But we know for a fact that our experience does seem to have this, begs this question, okay? So this sets up, not that the von der Mossberg model or later self-organization that we'll deal with is really going to give you a satisfactory answer, I would argue, okay? But I think this sets up like from the previous networks that we've dealt with, and then now we hit this point, and we are at the tipping point now. We are going beyond like what those previous networks were, feel sort of safe, we understand things. Now we're going into the realms of where, no, it's not so easy to explain everything. Where we felt like, oh yeah, now we know neural networks and we can explain how our brain works. Suddenly we hit this thing and we're like, wait, those ways of thinking seem to also have a limit here where we can't really explain what is this feeling that we have psychologically, okay? And so this setup actually is to lead us to this idea that the idea of genetics, determination, okay, versus the idea of biological plasticity. And the key notion of plasticity, we have to unpack a little bit, but what this statement means is this. Previously, when we talk about backprop and Hopfield, okay, we define the architecture, we define the activation function, we define the learning rule, which, if you think about it, if we can define it, it seems to be, it's pre-programmed. You can cook up some system like DNA, you put your DNA in some order, it will produce that protein. That protein will kind of go out into the cell and then be put in the membrane or whatever, which will instantiate the synapse, right? And therefore, the activation function. And therefore, if you have a synapse, you have the weights. And if you have a weights in a particular way, you have the architecture, etc., right? So up to this point, what we've described could be construed as sort of the, assuming that, if we have some base kind of functions or operations, we piece them together, we will get those complicated behaviors. And because these are functions that we can define, in some ways they're so-called, you can map them onto some idea of genetically determined, okay? However, there might be other things that cannot be genetically determined. What are those things, right? And we will talk about, and that's exactly what the von der Mossberg model will kind of exemplify, all right? But let's understand a little bit more about this contrast between genetic determinism and the notion of plasticity. When I mean plastic, okay, we all talk about neuroplasticity, right? Everyone is sort of familiar. Yeah, it's plastic because it's like we give you things to encode in your hippocampus, right? And then your hippocampus learns, you might argue that, oh, Hebbian learning is an example of plasticity. Yes and no, okay? I mean, I know the popular notion is that if you learn something, if you see things repetitively, your neurons kind of change their encoding ability, right? They will have long-term depression. Do a short note here. long-term depression, okay, or LTD, very common notion, and also long-term potentiation, LTP, right? Another common notion. And people tend to refer to these as sort of examples of neuroplasticity. Yes, in the sense that the neurons, their activity is dependent, well, their connection is activity dependent. And that's the Hebbian notion, right? That if you fire together, then you potentiate those connections, and then eventually one neuron is going to more easily stimulate the other neuron, and they're going to make new connections, okay? Yes, there's plasticity there in a sense of the neural architecture and the neural functions, the way they communicate, do not remain static. They change, and they change in a way that adapts to the environment. So there's that plasticity there, but the way that these changes occur is genetically determined, sort of, right? Like, you only see these so-called LTP, LTD things happening around the hippocampus, or at least in the way that we see, right? There's a particular way that LTD and LTP operate specifically in the hippocampus, but not in other parts of the brain. They have other ways of learning, or the way they do LTP and LTD might be a little bit different, right? But as long as those pieces are in place, you know that, okay, the neuron is going to, because of some calcium signaling or whatever, if you go down to the biophysics, the biomolecular level, then that creates more proteins which encourage synaptic formation. Those things are like, well, yeah, the DNA operates like that. So if you give it calcium, it's going to do this. It's not like it's determined mechanistically. Okay, we can see that. And that has nothing to do with the environment. It does not explain the cause of the environment, right? It only explains that because you have this DNA and your neurons react that way, if you stimulate this neuron this way, the neuron will have more than synapses, something like that. Okay? Appreciate this kind of the nature of this argument, all right? It is, from that perspective, not so much about plasticity. It's just carrying out its operation. And at the system level, we say that, okay, its encoding or its function seems to be plastic. But really what it's doing is just a determined molecular mechanistic operation. What I would argue is, but I'm not going to say that, that's not plasticity. In the field, we call that neuroplasticity. That's kind of like accepted. What I'm going to challenge you is that to think of what plasticity means is more like things that are not genetically or biologically determined. Okay? That from the DNA, you cannot explain why the biology does this. Okay? You cannot explain like just by looking at the organism's biological construct or makeup, you cannot explain why this biology or this psychological phenomena looks like this. Okay? So this is the key. And that's, for me, is like more about plasticity here, in the sense that it is not determined, and it has to react to the environment at large. And there is no way we can get this thing, this state, this plastic state, except to appreciate that it has something to do with the environment. Okay? All right, so there's that sort of a distinction there that I want to put here first. Okay, so and that's sort of, you see why this von der Mausburg's kind of question, when you couch it that way, is a little bit more impactful, because he was trying to explain exactly that there are some things about the biological nature of the way the brain is organized, or the way the brain works, that doesn't seem to make sense from a genetic point of view, or at least you can't see, like, why would you have this kind of organizational function in the brain? knowing what we know about the brain. The trick is you can't. You can't know about it just by looking at the brain. You have to look at the environment, okay? And in a very special way. Okay, all right, any questions so far about this setup? It's a bit more on the borderline of the philosophy and things like that, but I think, you know, it's quite critical to understand the significance of this work from the von der Marsburg paper, which is the 1973 paper, okay? To understand the significance of it in light of, if you put yourself in 1970s, what do you know and what you don't know yet, right? Now we know, we think we know a lot, right? But then maybe we are ignorant of a lot more things that we don't know yet. But back then, 1970s, more limited knowledge about how the brain works, okay? So in that perspective, you can see the profoundness of this work. Okay, any questions about this setup? Okay, so I have to build this up so kind of like to bring you to this notion that when, so at the end of the day, the key question is like, when we have a neural network and we can almost grasp almost everything about how it does it, you know, in terms of its architecture and functions, operational functions, we hit this brick wall of like, wait, there seems to be something we can't explain just because of that, all right? And that is, in a sense, like, if you drive down to the fundamental things, it is about whether it is genetic, whether we can define it in a genetically determined way, or we realize that no, there is no way, even no matter how hard we try, we cannot explain it, and we need something else, and that something else has to do with the environment and how our system reacts to it, okay? All right, so yeah, so, okay, so because of that, let's go to the von der Marsburg paper, and let me put that up. Okay, let's start with this one. Okay, let's go to the von der Marsburg paper itself, and again, I encourage you that all these Hopfield and the backprop papers, if you haven't read it, you should read it. I know it takes time because it's very dense papers, all right? And but they're good papers, and you know, and they're Nobel Prize winning works, so they deserve attention from you and time from you to sit down and understand and digest. Okay, now von der Marsburg basically starts out, and by the way, he was so this is 1973, and he was at the Max Planck. Okay, and so at that time, what happened? Huber and Wiesel happened in the 1960s, about 10 years before. Okay, what did Huber and Wiesel do? The first demonstration, okay, that if you put, this is their second paper. They had a preceding paper, this is 1960, I believe this one is the 1963 paper with the kittens. The first one is the 1972 paper with the one where the cat, and then, you know, they put the light rod, and then they measure the spiking activity. That one was more about contrast and topology. Like, if you put it here and it will, you know, the light bar goes, then it will spike. And it's also about like the neighboring contrast and all that. Okay, but here they zoomed in into something more interesting. Is that the light bar? So this is one you know, electrode. This electrode only fires. This is the same location, so it's not about topology or retinotopy. Okay, this is the same location, and so the neurons that encode for this location in space, they see the stimuli, or at least they are receiving the same light source or the light energy. But for some reason, okay, when you move it, the bar, and it doesn't matter, you move it this way, you move it backward, as long as the bar is at this angle, okay, the neuron is silent, okay? But if you tilt it a little bit, almost a bit more horizontal, and then you move it, this neuron fires, and it fires in a particular direction selectivity as well. It likes going up and this angle, okay? It doesn't like going down this angle, okay? And then if you tilt it some more, it becomes silent again. Okay, this is the first demonstration of orientation selectivity. okay? And now, you know this now, and it's like, oh, of course, you know, like, hey, that's how our brains are encoded. But you are in 1960, okay? You don't have computers so easily. You don't have Google, all right? So, you know, you got to appreciate this like mind-blowing moment. Like if you are Huber and Wiesel and you put it, you know, and you do that, this is like, wait, why? Why would your neurons like this orientation, that orientation, you know, that kind of thing? And that led to further work, and this is their later work, I think 1968, where you can see what they did was then they followed along the visual cortex, right? And from a start point, and they follow a straight line by sampling of the neurons further and further away from their start point. And if they follow the distance, they see like this interesting kind of linear progression here, okay? This linear progression, meaning that if this neuron likes this horizontal line, its neighboring neuron likes slightly deviated off. And the neighbor of that likes a bit more deviated, and the neighbor of that, you know, more. So you can see, this tells us, okay, the fact that you have this smooth curve here, and rather that, as you go along a straight line, rather than things jumping all over the place, this is this kind of higher level derivative of discovery of that, right? This detects that some neurons like some orientations, okay? This detects that the neighboring neurons like close derivative orientations, and they are organized in a smooth way. It's not like jumping all about. Okay? Again, go back to 1960s. Seeing this kind of thing is really groundbreaking, okay, at that time. Eventually, we get higher, this is work by Bosking in 1997 now, okay? And eventually, when we get better techniques, right, we can get like, you know, we can scan a big array, not just limited to one electroencoding, and then we can get things like activity from the images, right? We can do image the activity of the patch of neurons that we are recording. We can see that when you stimulate V1 neurons like this, you get this kind of activity pattern. When you turn the orientation, you get this one. When you turn this way, you get this one. When you change this way, you get another one. When you look at it like that, gray and black, white and black, right? Grayscale image. You don't really see anything interesting, but they very smartly use different color codings. Oh, I hate that. Why does it keep doing that? I'm going to use the pointer. It's not pointer, that's pointer. Okay, let's turn it on. Oh, is it dead? Okay, yeah. So if you color contrast this, code it as different colors, and you put them over each other, that's what you see. Basically, this zoom in, you see this graded smooth pattern, right? Which is the same as essentially this one, okay? Just not in terms of just one recording at a time, but in terms of like the whole patch. You can see basically if you follow a straight line, you will see this kind of pattern. And at certain junctions, you get these spindles, these centroid points, okay? Where it will kind of rotate. If you go rotate around these, you will also sort of see the changes in the orientation selectivity. So basically each color means that that neuron that's coded in that color prefers this orientation as opposed to other orientations, okay? So this is the phenomena that, now this one is demonstrated in 1997. So, but this is kind of like expanding on what Huber and Wiesel already knew in 1960s, okay? All right, so put this in context, yeah? And appreciate, therefore, when you are von der Mausberg, in 1973. All you had was Huber and Wiesel's cat study. Basically, all you had was this figure 2a, okay, in 1973. All right? He is, in 1973, and you can demonstrate, this outcome from a modeling point of view, which is, what is this? This picture, figure 10 in this paper, is this picture, right? This figure 1 in this paper, which is 1997. Okay? So appreciate this connection here, that this is 1970s based on 1960 work. Now we have our imaging and fancy methods, 1990s. We can see what they already show you from a computational point of view, that's what's happening. Okay? All right. So this is to give you the story and the history of it and the, the methods of what was doing. How do we link it back to what I was talking about in terms of the difference between genetic determinism and the plasticity, right, which cannot be determined by the genetic substrates? It's because the motivation for von der Mausburg, why he wanted to instantiate this model, is precisely that if you read his paper, at least the first paragraph, the questions he asks is precisely that. Why do the neurons organize themselves this way? And when he say, why do they organize themselves this way, he's talking about Huber and Wiesel 1960s work. Why? Why does this happen? Because of all we know about the way that cells are made, and how even neurons, they knew about neurons, how they connect to each other, cannot easily explain why we see the Huber and Wiesel figure 2a. There's no way. It's not even easy. It's impossible. Okay? So the question that drove von der Mausburg was that, has it got something to do with the way that the neurons are organized by themselves? Not about those biological properties, but because these neurons are somehow, these V1 neurons are like growing together like this, right? That therefore, what we see, the Huber and Wiesel figure 2a, comes out from the way the neurons work. Okay? So by that logic, von der Mausburg is saying that if we do it, if we put neurons together or neural units together, and we let them do whatever it is they do, we make some assumptions about what they are doing, and we put them together, that therefore we should see figure 2a in a computational sense. Okay? So it's a bit mind-blowing, right? If you put yourself back in that time frame, it really is. All right? Or at least, like, if you make this connection, for me, it was quite like, wow, this is before any of us were born. And it's not so far away either, so it's pretty cool that it was at around these decades that, wow, we really know how to do science. There are really some cool scientists out there, okay? Okay, so this is the setup, and this is the mission, that we have neural networks that, or at least we observe that when neural networks operate in the way they do, okay, in the specific case of orientation selectivity of V1 neurons, we get some sort of an observed organization that seems to be governed by itself. Not by, in a sense that, itself in a sense that not from the biological sense of the self, but that the way these neurons work, they seem to have this emergent organization property. No one taught it. The genes didn't teach it, okay, to be this way. They just kind of on themselves, by themselves, organize themselves this way. And hence, the idea in the title of von der Mausburg's paper, that this is this examining on the self-organization of the orientation-sensitive cells in the visual striate cortex. Okay, so this is the big picture here, and so this is about self-organization. Self-organization. All right. Okay, give me a second here. I'll put this up. All right, and specifically now, how are we doing on time? Okay, very good, 10 minutes. We're going specifically, okay, oops. Specifically, I don't know why my spelling is a bit weird this morning. So I have a hard time spelling things. Maybe I'm getting dementia as we speak, which is highly possible. So specifically, we are targeting self-organization okay, of the V1 cortical columns. Okay, that's what all just now that figure with the colors, right? That's what those are. It's like your. So imagine you are. So if you have a sensor, right, and this is the V1. This is the V1 gray matter. Okay. Okay. So that if you track, if you move, well, you are able to see this array here. So what you would see is actually attempt to do some color, okay, like this, right? Okay, so like, yeah, or so if this one likes this one, this one likes this one, this one likes this one, and this one likes this one. And then, of course, after green, you go back to blue. Okay, so that if you were to scan top down, if you look down, you see what was in that colorful picture just now. Okay, like you have these rainbow color patches. But essentially, if you cut deep into the gray matter itself, what you see is that the thickness on the thick aspect of the V1 gyrus, it's like through the whole column, they are having the same selectivity for the orientation. But if you move to the neighbors, you get this changing of the directions, right? Okay, so this is what we are trying to model. This is not determined. Right? Nothing in your DNA is going to tell you that it's going to be like that. We have selectivity for whether you are going to differentiate into an astrocyte or a neural cell or a glial cell, right? But we do not have in our DNA any signal to say that, oh, you are going to be a horizontal line cell, a 60-degree cell, or a vertical line cell, right? Nothing in our DNA tells us that. It is self-organized. This phenomena is self-organized. So can we model it? It is a neural network. can we model it? We can model hot field, we can model backprop, some sort of error learning system, okay? Can we model self-organization phenomena? And of course, the fact that we have von der Mossberg paper means that we can. And so how do we do it? And so this next 3 courses, hey, sorry. Okay, sorry about that. Yeah, so if, where was I? Yeah, so we can instantiate this model, all right? And we have von der Mossberg that tells us that how to do it. And so for the rest of this course, that's, I guess for the next 2 or 3 weeks, that's what we'll try to do, okay? And it's difficult, okay? Now, it's difficult not because of the model programming itself. It's difficult because of the cause that I'm talking about. So, so back to the cause. Recall, oh, sorry. So let's say recall cause, the notion of cause, okay? What caused this? Okay, what caused here is something to kind of like introduce to you. Okay, another concept. Okay, because it is something to do with this one. This one. Okay? Things in the physical world are not arbitrary. This is going back all to the beginning here. Things in the physical world are not arbitrary. Our system, we feel like we are always trying to find an explanation for what's causing our experiences. Okay? And so therefore, we assume that our experiences are not arbitrary, and that begs the question of what's causing it. From a physical point of view, a very, very first principle, very, very basic notion of cause, okay, implies binding. Means the one state must depend on another state. So it's a very Markovian thing. We kind of talked about it, okay? And at the very, very heart of it, why are two, if we go back to visual stimuli, why are two states bound to each other? Okay? Why are they not arbitrarily like, oh, this state and that state? They could be existing in anywhere or in any way. There's no rule binding these two states. Okay? The suggestion is, if you think about it, there's a lot of philosophy and physics behind it. I'm going to give you a shortcut here, that all this is about space. And by that token, it is about distance. Okay? The fact that your visual system has to encode this location is here, and this location is here. Therefore, they are separated by however many meters. And this is absolute. This is not arbitrary. Distance, the ultimate non-arbitrary binding. Okay? That insofar as we know how reality works, you cannot run away from this fact. So far no one has, right? Okay? That it just takes X amount of time for you to get from this location to that location, unless you can teleport. So far, no such thing. Well, maybe they have some very, very special case. But it's like, in general, at least from our psychological visual experience, no one has ever suddenly appeared out of nowhere from somewhere else. Okay? They took some time to get there, to that position. Okay? And that is about distance, and that is about space, right? Okay, so space is the ultimate binding here, or distance, the equivalent, all right? So I propose to you that the reason why the self-organization happened is because the neurons in this patch are encoding the different orientations in this location. And the neurons in the next patch are encoding the orientations in a bounded spatial location, distance, okay? And because there's this distance map of different orientations, right? Then as you move along, you get this kind of like, that's what you get, okay? You'll get that nice smooth orientation columns of different orientations at different distances, okay? And because of the neurons' retinotopy and sensitivity to spatially bound stimuli, by definition, visual stimuli are spatially bound. Therefore, the V1 cells function are spatially bound too. And therefore, you get self-organization. Smooth, not arbitrary. They are smooth, therefore they are not arbitrary. They are spatially bound, right? Okay. Now, all this might seem obvious to us, like when we see, oh, of course, yeah, the V1, they are like having these columns and they are graded and all that, and we all take it for granted that, yeah, it all makes sense and all that. But when you are challenged, I ask you to sit down, explain to me why do you think that this makes sense. Okay, you have to go through all of that. This is the reason why it makes sense. So this is about articulating things that, or you probably feel very intuitive when I give you the results. But to get to the results, to understand and to explain them and to like make the links, yeah, you need to sit down and be very, very clear about what you mean by, every concept and what the neurons are doing, what the function means and all that. Then you can express it. And if you can express it, it suggests that it makes even better sense inside. Okay, so this is part of that training too. It's like you kind of have to, it's not just, oh, I see this and everything makes sense and it feels good, then full stop. It's about like, do I really, really understand it so that I can formally describe it and in a very concrete way, because that is the requirement if you want to make it into a model. Your understanding has to be very concrete and formal and so that you can model it. Okay? All right, so it is about distance, physical distance. In other words, so our model has to have distance constraints. Right? You see? If you develop all this, you kind of give yourself the solution in the end. So in other words, if we want to do self-organization, something about the way we design our model has to incorporate the notion that there is physical distance constraints in the model. Up to this point, we don't have it, right? Because up to this point, so far, our model is like, fully connected, isn't it? Like, everything is connected to everything, okay? What we need instead, is going to be something like this one will connect here, this one will connect here, this one will connect here, okay? You see? Different. Okay? That's essentially what the von der Waals-Brooke network will be doing. Okay? And we'll talk more about that after the break. But this is the conceptual distinction from the hot field and from the backprop applications that we've been doing, which is the one on the left. Now we are going to be, because of the reasons that we have developed, we are going to be doing the one on the right. Okay? And how do we do that? It's actually not so hard to do that, but as I said, the difficulty is in about representing the spatial stimuli input and encoding itself. The architecture of the network is actually okay, all right? Okay, any questions? Just setting this up, very conceptual, abstract space first, principles first, as always. And then next, I'm going to, after the break, we'll have a break, and then after the break, I'm going to draw out the model, architecture, and the functions for you. And that will be today's class, is to establish these theories first. Okay? Any questions about the motivation, the history, the background? Interesting? I hope it is, okay? Because really, if you go through that, it's the first time you deal with these papers and you make these links is quite profound. Yeah, it's not something obvious, but if you are the scientist and you put yourself in there and the history and the way these logic all just come out, I think it gives you a model of how to understand things even in the future for things we don't know yet, where we are now and how we piece things together and how we do our science, at least in the modeling world, right? Why we do it, how we do it, what we can do, some ideas for you, how to approach problems. I think beyond just learning the facts, we are learning a set of approaches, right? And logic and ways of thinking, reasoning skills. So I think this is more important actually than the actual thing itself, okay? All right, let's take a break for, I might have to do something, so give me 15 minutes. Actually, let's come back at 10:30, okay? So about 25 minutes. Let's have a nice break, and then we'll come back because the second part will be relatively short, all right? So, well, we'll see, okay? And we'll pick it up at 10:30, okay? Right. Okay, let's start it up again. Close that door. All right, we're gonna dive into the von der Marlsberg network architecture and see how to create a network, or how he set up a network to solve the problem of explaining how V1 neurons or the V1 cortical tissue exhibits cortical columns that have orientation selectivity in the way that shows that graded smooth transition of different sensitivity to different orientations, and thereby explain how that phenomena of having self-organization might be modeled, okay, might occur. And as with all our approaches, we start with first, before we even talk about the network, let's talk about the stimuli. And the stimuli, if you have the paper, you can pull it up on your screens. The stimuli in question, the data table in question, okay, are these. This is the data table that we are talking about. I'm going to use, I guess I should use red. It's more obvious, okay. Okay. This figure 5 here is actually the data table that we want to evaluate, that we want to use, okay? And what are these? These are, imagine, if we talk about this one shape here, let's focus on this one shape here, okay? How he's set up the problem in a tractable way that you can model using neural networks is to first reduce it to, well, we are talking about orientations, and we are talking about orientations at a particular location in space, okay? So let's not worry about a lot of areas in space. Let's just worry about one patch first, and the fact that in that patch, at any moment, there could be different orientations at that location, okay? All right, so this one hexagon patch represents one location, a specific location in space, okay? Now in this location, he realizes that if you want to talk about orientation, you have to have, first, orientation that by definition means it's not a one-point thing, right? It can't be like, you can't just be focusing on this one dot here, okay? It has to be a set of local, as we said, spatial bindings, okay, that determine the orientation, right? So you have to have a set of units representing this patch. It can't just be one unit representing this patch, okay? So, and in fact, he's kind of used a very economical geometry to do that. He uses the hexagon. The hexagon is efficient. It's an efficient way of encoding local orientation. And this is what constitutes the data table. He uses this format, okay, to encode the data table in order to encode the orientation. And it is efficient because if you realize the hexagon is equipotent in terms of the distance to the corners, okay? And you can imagine that if I have a few hexagons, right, you can stack them up. Any of you play board games? So hexagon tiles, right? It's very efficient. Why don't you use squares? Squares are actually not so efficient. Okay? And if you use circles, you'll get those, you will have, you know. And what about this part, right? You get this problem. And triangles are okay, and so you get vertices, but it's like you don't get that nice like representation around a centroid, okay? Because it's only three corners, right? So you realize actually that, he realized actually that the hexagon is the most efficient shape to do this, okay? If you use any other shape, you get biases because of the empty spaces you can't fill in, or you have to overkill with many tiles, right? Or you have inefficient usage of the space in order to represent how one smallest unit of location of point coordinate might be connected in an unbiased and efficient way to the next one, and that you can tile it infinitely. So for that purpose, we have to use hexagons. And that's what I mean is the pain, okay? It's not really so much the network itself. The network is okay. But to encode things in hexagon, how are you going to encode a data table for hexagons? Let me ask you. Think about it, right? It's tough, okay? I had to think about it a long time. We are used to thinking about things in squares, in grids, square grids. So this is x, this is y, and any point on it. Okay, this is x1, y1 coordinate, right? How to do hexagon? Okay, we'll get to it. Okay, but I'm just presenting you introducing you to this realization. We realize that a hexagon is ideal for representing like a given patch of space with some orientation features in it, okay? But later on, we come to this problem, but wait, how do we code it really, all right? But let's take the concept first a bit further, okay? So let's assume that a hexagon is, as we say, most efficient, and we can use it to encode orientation. How does he encode orientation and in an efficient way? Well, you can already see it right in these figures. And he's reduced it to the bare minimum given the hexagon shape. How so? Each hexagon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay? Each hexagon has 19 units. In question. And there's always just 19 units. Okay? But this is the input data table, by the way. Okay, obviously. Right? So the input consists of inputs, which is actually a 19-unit vector. Okay? This is a 1 by 19 unit vector. Okay? And this is either on or off. Bigger circle means on, smaller circles means off. Okay? In other words, if I were to encode it as a vector, and I go into the vector here, I would say this is unit 1 is off, unit 2 is on, unit 3 is off, unit 4 is off, on, off, 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 on, off, off, on, off, on. This binary word encodes a vertical line in a hexagonal projection. Make sense? Okay, so you can work it out. What about stimuli patch number 2? You just change that, right? You just change that, and you would get a slightly tilted line. Change that, get even more tilted, etc. Okay? So in other words, this input data table is going to have if we skip first the problem of the hexagon projection, this is going to be a 9 by 19 array. This is going to be your input data table. Okay? So it's different, right? Different from previous one. It's like kind of like almost the same, but not really, okay? And it's creative, quite creative usage of coding approaches, okay? Can we see that if we first assume that there's some way to project into a hexagon patch, each patch has 19 units in order for me to represent this, this, and this is this one, and this is this one. So let me, not to make things confusing, this one. Right? Okay? If you use 19 units and each unit is either on or off, and the lines can only exist in these 19 units, and they have to be straight lines, then you only have these 9 possible sets of inputs to encode all possible orientation. Think about it. I can't put this here. It would be weird, right? It's not encoding anything in terms of the change in orientation. And I can't do this. It's weird also, right? Correct? So he's made it very, very economical such that you only need these 9 stimuli. And it's important for economy here because then it's complete, right? Because if you say, no, he's missing some possibility of other on-off states to encode some other orientations, okay? Then you should add it. Then that should be part of your training data set. But in doing it this way, these 9 sets, they represent complete orientation, possible orientations, given that the discrete units in this hexagon patch have either on or off states, right? These discrete unit states, if you have these 9 patterns, they represent complete possible orientations that we want to train the network on. Okay? So this is very neat because of this reason. When he uses this way, and he uses this representation, and he uses these 9 sets, these 9 sets represent complete input data you want to train the network for the possible orientations that this network might experience. This is important. Obviously, we know in our experience, we have much more orientations than just 9 orientations, right? But for a simple modeling problem, we want to reduce the problem to be as simple as possible so it's manageable, it's tractable, easy to do, implement. But at the same time, it has to be compelling for reality, right? So in our reality, we have all possible orientations. In this network's reality, these are all the possible rotations that this network will experience. Any other combination or pattern will be extra stuff, not fundamental. These are the fundamental 9 possible orientation states given this format. Okay, so appreciate this. We have an input data table array, and it's going to be a 9 by 19 input data table for the reason that in the hexagon, we have 19 units, and we have 9 possible states. And the 19 units, if we change it to a binary vector, look like that on the upper left here, okay? And by changing this, we get the 9 input sets, okay? All right, and that's how you apply the orientation input stimuli. Okay, so we have the data table now. What is the architecture? The I'm going to call VDM model architecture. You will instantiate, I'm going to draw this here. These are 19 unit. Call it K, okay, 19, K1 to K19, okay? And this is the retinal, he calls this the retinal plane. Okay, because he's trying to say like on the retina, on the eye itself, there's this patch of neurons that receives the input from a resolution of 19 dots in that space. And in these 19 dots, this patch will encode the orientation that it sees at that location, okay? And if you realize it is going to be, and this is important to appreciate, by definition, if you have a hexagon and you have 19 units, then it's going to be 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3. It's going to be 3, 4, 5, 4, 3. That will instantiate your hexagon patch, okay? Your retinal plane. Then, so in other words, you are going to have A, S, K. This is going to be a 1 by 19 vector, input vector. And this input vector will go through 9 different states, according to the data table we talked about just now. You will instantiate this input layer like this, okay? Then, again, we haven't talked about the hexagon projection yet, but let's assume that this is a vector, a 1 by 19 vector. So this input vector, you will instantiate, okay? Then we are going to have a remember, we are interested not in the retina, we are interested in the V1, the striate cortex. So it's going to be a bigger piece of, a bigger tissue, all right? So we're going to call this the cortical plane. And it's going to be the excitatory layer. Okay, and it's going to have 169 units. Yes. And we're gonna have, it's gonna have H. And we're going to call it excitatory units, E units, okay? And oh, by the way, we call this S because it's the stimulus input, S units to the E units, the excitatory layer, okay? And it has 169 units because, let me check here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, 15. It's going to be 1, 2, 3, 4, 5, 6, 7, 8. How to draw 15? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15, okay? As the width. 1, 2, 3, 4, 5, 6, 7, 8. 8 as the edges. 1, 2, 3, 4. So the width will have, I'm going to make a little note here. It's going to have 15 unit width. Okay, whoops. And it's going to have 8 unit top boundary. Okay, and if you do like, so at first it's 8, then the next row will be 9, then 10, right? Then 11, 12, 13, 14, 15. Okay, then it'll be 15, 14, 13, 12, 11, 10, 9, 8. Like that, that will be a hexagon of 169 units. Okay? So in other words, this will be A E R vector, and it's going to be a 1 by 169 layer. Okay, 169 unit layer. Okay? And it's going to take inputs from, so a given unit, I'm going to emphasize given unit here, okay, is going to take okay, I'm not going to draw it because it's going to be very messy, but this is going to be W WSE. I'm going to use white, okay? Right? And WSE is going to be a 19 by 169 array. Make sense? So every unit in the excitatory cortical plane layer will take input from the 19 units of the stimuli retinal layer, resulting in, because it's that fully connected in that sense, it's going to become a 19 by 169 array of weights. Okay? Now, another thing is it's going to have mutual excitation as well. So what's going to happen is each unit okay, etc. Okay, let me emphasize that this is etc. Okay, so all is going to be fully connected that way. So such that the at the excitatory layer, each excitatory unit will also receive input from its other excitatory units, so that you are also going to get what we call W excitatory to excitatory. So that it will be, what is that? Okay? Easy enough? Okay. Here's the trick. And here's where there's some brilliance here. Von der Mausberg realized that in the V1, a critical, this one we can see biologically, histologically, that there are what we call interneurons. And they are what we call GABAergic, meaning that they operate using the gamma butyric acid neurotransmitter, and because of that, they have inhibitory roles. And in fact, the way they work is like this. Okay. This one. You get these columns. They stimulate like deeper or more superficial in a column. But between columns, you get these interneurons. This is a very rough geometric picture. It's much messier in the biology of the brain, okay? But roughly, you get these within column transmissions, but between columns, you get these interneurons, and they are GABAergic, and they are inhibitory, okay? So he realized that there's this real biological architecture happening. So what he did was to create a cortical plane inhibitory layer. Okay? And I mean, in fact, it inhibits because it itself, you know, if you activate it, its effect is to inhibit the others. All right? So it's like this inhibitory. Well, it's inhibitory. Okay? Right. So there is this mechanism happening such that if a neuron is active, the net effect is it will suppress other neurons. Okay? So what we call, this is what we call a winner takes all system, WTA. Okay? If I win, you all lose. If I win, I take everything. You all have nothing. All right? It's a winner takes all network. Okay? So that's essentially where this idea comes from, and like this is how it's instantiated and how it makes sense biologically. There are winner takes all networks in our brain. Okay? And it is instantiated using this cortical plane inhibitory layer, and in it there are also 100, similarly, it mirrors. It sort of mirrors the excitatory layer. So you can imagine in your gray matter, it makes sense because in the gray matter, okay, so let's say this is deep. Sorry, no, this should be superficial. And this is deep. Now the white matter, and this is space. Okay? That you have within one column, okay, then another column, you have these interneurons, okay? But that they are kind of, because you have the same columns, you also have interneurons. So you can see that they are sort of meshed together. So as big as your excitatory layer is, your inhibitory layer will be at least the same size, if not bigger, or depending, right? But they should, the point is that they are intermeshed together. So he instantiates it by having a inhibitory layer that's basically the same size, and they are located in the same overlay over each other. That's the concept of it, all right? Such that, we call this I units. Inhibitory units. Okay, and we're going to use the node index denoted by Q, such that this is going to be A, and it is going to receive, it's inhibitory unit. Let's sit down here. Okay, and it's going to be 1 by 169. All right. And so AIQ is a vector, 1 by 169, and it receives input from the excitatory neurons first. Remember, winner takes all means if I am active, I'm going to tell you to inhibit everyone else. So, but first I have to be active. For me to be active, I have to be activated, right? Okay. So it is going to take, I'm going to use blue color for inhibition. Blue. So anything that's kind of hot means it's active. Anything that's cool is to suppress, okay? So if this neuron, again, the highlighted neuron in the excitatory layer, okay, what it will do, well, I should draw this. So it has the same. So it's 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15. Okay? So, and you can fill it up with the corresponding rows and all that. But each excitatory unit is going to project to sort of okay, dot, dot, dot. Okay, it's going to project this way such that you're going to get, this is going to be the array W, E to I. So the order of the index of the arrays are important. S to E, E to E, E to I, and it's going to be also a 169 by 169. Okay, and now I'm going to use a slightly different theme because it is inhibitory, but it is a kind of a stimulation here, okay? Because then each inhibitory unit sends so colorful. Okay, dot, 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 etc. You fill it up yourself. That such that this is going to be E, W, I, E, and it's also this is the fundamental architecture part 1 first. There's still more. Any questions first about this part? This is the fundamental setup first. Then there's some tweaking to do on this. It's essentially how von der Mausberg did it. So we are just basically trying to copy his paper. I think it's hard enough, okay? So actually your third assignment is just to copy the von der Mausberg network. If you can do that, you're done. Not even asking you to say, okay, so now use this to try and do whatever evaluation, which, you know, we're trying to, what we do with the hot field and the backprop and all that, right? It's like, okay, you do it, and then after that, you kind of expand it, right? If you can do the von der Mausberg network in and of itself, I mean, I think that's already pretty cool. So, you know, all we're doing here for the third assignment is just to copy the von der Mausberg network, okay? But this is it. This is, so if you read through the paper and you spend time to digest it, you will end up with, this is how he modeled it, okay? I mean, this is what I had to do, right? It's basically read the paper and basically translate to doing it so that you can do it yourself. You set up a retinal plane, okay, 19 units. Then after that, you have an excitatory layer in the cortical plane, which is the V1 or the striate region, and it has 169 units. Okay, the reason why it's now expanded to 169 is because if you realize, okay, so again, if you have a hexagon and you want to kind of make another hexagon shape, okay, in this, but a bigger one because you want it to be expanded, right? You realize that the next economic scale from 19 is actually 169, all right? Go and think about it. You can't have a smaller hexagon and then be able to encode this 19 units sort of fairly. So again, these numbers are not chosen for fun. These are very economized, if you realize. Okay, they are the minimum sizes of these hexagon patches to encode this 19 units in the next up level of a bigger patch. So he's not, in other words, he's not arbitrarily deciding that there should be this size. He's realizing that, well, V1 is at least higher up than Retina, right? And it's going to be like a bigger patch encoding for one small thing because there's more information to encode, right? But by how much? And by, should I do 1,000 units? Should I do only 500 units or 2 or 20 units or whatever? No, he's very reasonable, and he says that, well, given that my input is 19, the next bigger and unbiased hexagon shape is 169. So the sizes are all making sense here, okay? And it could be more, because V1 could be more layers away than the Retina, for sure. Well, then you just scale up accordingly. But all he had to do is to demonstrate one step of a scaling to show that. Because actually in lateral geniculate or superior, we also have orientation selectivity. So let alone in V1. So it's sufficient. In what he's done now is sufficient. That basically 169 units as a next up efficient expansion from the 19 unit encoding. And you get this array then. WSE, stimuli to excitatory layer, is 19 by 169 array. And then you have, and so this is the excitatory units vector. And then they project to the inhibitory units using the array W excitatory to inhibitory, which is 169 squared. And then the excitatory units project back to the excitatory layer. Okay? Now, if you see this, you will realize that if I'm talking about this, unit here, which is going to be, let's talk about its activity. How do we calculate its activity? Let's calculate its pre-activation state. Okay, the pre-activation state of the yellow unit in question is going to be, it is unit, sorry, not S, E. For unit S, the activation state are the data table, right, the orientations, okay? It's either on or off, and we set it, okay? But for the excitatory layer, it's going to take excitatory layer unit H at time t, okay? And we're going to say it's pre-activation, so we put a prime there because we haven't applied a nonlinear function yet. We just say, let's do the summation. Remember, pre-activation is basically the weights product with the activity, and you sum that, okay? It's equals to, if you go according to this architecture, you will note it is basically K, W from the stimuli to the excitatory layer multiplied by the input retinal K unit, right? So this orange part here will be feeding into the yellow unit, highlighted unit's pre-activation state. But that's not all, isn't it? Look at that yellow unit. It is also receiving from WEE and WEIE. So, plus. It's all summations, because the summation of this plus the summation that it's getting from another set of arrays. But it's still a summation, so it's very easy. Okay, it receives from the excitatory layer, from the other modulated by it receives from the excitatory units modulated by the excitatory weights, excitatory to excitatory weights, and it's inhibitory now. It receives inhibition, negative, sum of Q of all the inhibitory to excitatory modulations of the inhibitory neurons, units. Okay, so this is the pre-activation state of the yellow unit. And we're running out of space, so I'm going to, no, I will change, I will not erase it because it would be very troublesome. So what I'll do is I'll move this a little bit. Okay. Now, then, so far, it's okay in the sense of this pre-activation. So we're not talking about the activation state yet because that's very easy. That's just the activation function, okay? The nonlinear activation function, which we will apply on any pre-activation state, right? So the key is the pre-activation state first. So here, the pre-activation state for the excitatory unit comes from the input layer, the sensory unit, and the inhibitory unit, and also itself, the excitatory unit. So the summation of all this, or the negative summation from the inhibitory, all culminates in the pre-activation state of the excitatory unit. Okay? Now, then, this is fine and good because we know this. This we know. And the other excitatory units, because they receive input from the input layer, the sensory layer, this we also know. But this one, the activity of the inhibitory unit, where is it so far? So far not incorporated. So we also have to know what this pre-activation state or what its activation state is. So another part of the equation is, and because it's blue, I'll use blue. So let's talk about this blue unit's pre-activation state. Okay, that's going to be IQ at time t also, I suppose. It's going to be equals to the sum of R H. Okay, from the excitatory to inhibitory layer, and let's make sure it's I and A, H, excitatory unit H. Okay, seems simple, but, and this is where I say there's some tweaking, okay, such that, and this is where the idea of distance spatial binding comes in. And I will talk about what is R in a bit. But there's going to be, what this means is such that, so this totality here, okay? So let's make things clear. Oh, and in fact, actually, I should use this in white because this applies not just to the inhibitory layer, it applies to everything, okay? Such that W E E is equals to 0 for H R greater than 2 First, there's more, but let's unpack what this means. The pre-activation state of the excitatory units is the part in yellow, which led us to ask, well, what is the activity of the inhibitory unit? Well, the inhibitory unit's pre-activation state is in blue, okay? And seems to be, if you have that, then you can get the inhibitory activation if you apply the activation function, and therefore you can compute everything. But there are some qualifications, and the qualifications such that the weights that are in the excitatory to excitatory layer are set to 0 for if the unit that is receiving, the H unit, okay, is R greater than or equals to 2. R is a distance. Where am I going to write it? Here. Note that R is node distance. Node distance means you have to do some geometry. Okay? I'm going to put this here now. 19 by 169. Okay? So that I can have this space. I'm going to expand one portion of the hexagon, okay? And let's call this unit 1, 2, 3, 4, 5. Okay? This is going to be 1 distance. What is this distance? You can calculate it. You have to use geometry. This is where I told you this really is the problem. It's a real angle, okay? It's physically bounded in real space. Okay, you're not kidding here. It is not a simulation. Here is where physics. I mean, there's some simulation, but the notion of distance is relatively real. Assuming the nearest neighbor in the hexagon, if you have the hexagon expansion here. So like this node 1, 2, 3, 4, 5 is 1, 2, 3, 4, is maybe this one, right? Okay, so this is that pink patch there. Okay. Given what you know about hexagons, you know what theta is. You can calculate theta. Seriously, you can. Okay? And if you can calculate theta, and you assume that the nearest node distance between node 1 and 2, which are the nearest possible node distance, right, in this representation, you can also know R of 1, 4. So R of 1, 2 is equals to 1. What is R of 1, 4? R of 1, 5. You can calculate R of 1, 3. You have all the R's of all the nodes to every other node. You can calculate that. So that's what R is. Okay? If the distance of a given node to this so-called target node in question is greater than or equals to 2, the weights are 0. So in other words, think about it. The only units that can excite in the excitatory to excitatory layer are its neighbors. Anything that is beyond its immediate neighbor has 0 influence on you through the excitatory path, to the excitatory path. Okay, does this make sense? This little qualification, this little adjustment to the WEE. Okay. Another one, such that WEI is also equals to 0 for H also. Same thing. But so it applies to WEE and it also applies to WEI. So in other words, the influence of an excitatory unit is only to its neighbors. It does not excite in the excitatory layer as well as in the inhibitory layer. It does not excite units more than distance 2 away, whatever the unit scale is, right? And the final one is also the inhibitory layer to the excitatory layer. Now this is different because, because these are interneurons. Interneurons are not just kind of like excitatory, like in terms of their local connections. They connect kind of skip one away, sort of, right, in the way that they are organized. Because of the organization, we show you here on the right. So that such that Q, because it's about the inhibitory units, is a bit different. Okay? Skip one neighbor. And also, use that, like, skip one neighbor, the neighbor of my neighbor will inhibit, okay? I will inhibit you, but I won't inhibit my neighbor, and I also won't inhibit beyond the neighbor of my neighbor. That's what this means. I only inhibit the neighbor of my neighbor. Okay? Now, what does all this mean? Because this is neurally plausible. Our neural dendrites do not connect so far away. In the cross-cortical, between column range is restricted, right? Correct? And it is instantiated in how far you are using the R variable, right? Your between cortical range is restricted because your dendrites don't go so far. The only way your neurons can go really, really far is through axons, okay? Your dendrites might spread out quite a lot, but ratio-wise, its range is still relatively restricted. That is the organization of our neurons, yeah? And so this is instantiating that. Okay? So with these qualifications, you will be able to set up the architecture. The von der Malsburg architecture is set like this. Yeah? How did he determine this? Yeah, because he knows that the nearest unit is 1, okay? And you will find that if you calculate this unit is still less than equals to 2. This one, it will be greater than 2. So he's basically defining it that, if I were to erase this part a little bit, okay, this hexagon this shape, this is R less than equals to 2. What he's saying is when he sets that the R is 2, okay, is such that by the hexagon's geometry, only the neighboring neurons will influence you, or the neighbor of the neighbor neurons, but not beyond that. So this 2 just falls neatly according to the scale, of course, right? But the 2 is set there so that by a hexagon geometry, you effectively filter out only your neighbor or your neighbor's neighbor, and then beyond. Very easy, very neat number. That's how you determine. If you make the R requirement not 2, like 3, then you go wider, right? And you can't go less than that because that's effectively nothing. No neighbor, just yourself. Okay? So that's this R parameter, the requirement-wise set at so-called always going around greater than 2 or less than 2 or equals to 2. Why always 2 is because of the way the hexagon, when you quantize it like that. What we say, this hexagon has been quantized because it is discrete locations in the hexagon, that if you calculate the geometry of it, the radius, the distance of one unit to the next can be effectively defined using 2. As if you want to filter its immediate neighbors. If you go to 3, or you have to find some other, you can calculate geometry, maybe 3 is not, maybe it has to be 4, I don't know, I have to calculate the math behind it. Then effectively you filter the neighbors' neighbors. Or you go to 4 or whatever number, then you filter the neighbors' neighbors' neighbors. Okay, the full width f hat maximum actually, okay? So this defines the full width of half maximum. If you go back to Gaussian signaling, that how far away you want your neighbors to be able to influence you. 2 is the setting in this Gaussian setup where it will only be your immediate neighbors. It's a great question. Yeah. Any other questions? Yeah. The red line, the blue line, and the green line here. Okay, that's fine. So the red line is WEE, okay, which are that if I draw arrows, maybe it will be a bit more obvious. So if I draw, so for the orange line, the arrows are all this way, okay? Okay, so these are all inputs from retinal plane to excitatory layer. Okay, so the orange line are inputs this way. That's why the pre-activation state you see, this is the orange WSE. Okay, all right. Then the red ones are the inputs of the excitatory units to an excitatory unit. So within the excitatory plane, and that's this one. And you can see they are taking the activity of other excitatory units, yeah, taking the activity of other excitatory units, modulating it by the input to a given target excitatory unit, okay, such that the orange times the ASK plus the the red times those AEHs, okay, those will influence those are part of some influence on the yellow unit. Okay, does this make sense? Okay, then finally I'll talk about the blue. The blue one, on the other hand, are going this way. Okay, they are going to the inhibitory units, so they are here. So yeah, the blue one is already in blue. Here, the blue one, okay, are talking about a given inhibitory layer. So let's talk about this one. Okay, is receiving. I mean, I'm drawing this as going out, but you can reverse your frame of reference. And if I were to focus on this, it is also receiving all the blue from the excitatory layer. So that's for any given inhibitory unit, it is receiving the modulated excitatory layer activity, AEH, modulated by WEI instead, okay? Then the green one is the inhibitory layer going this way, okay? And again, you can say that I'm taking this now from the perspective of the inhibitory layer sending out weights, but you can imagine that this yellow unit is receiving the green weights, right? So that this is that green part there. Does that make sense? Okay, yeah, so the arrows probably help. Let's make this a bit prettier. I'm going to do this. So I use the color will probably help everyone a lot more. If I use orange, this is WSE. If I use red, this is WEE. Okay, and then if I use, was it blue? No, green. Yeah, this will be WIE. And I'm going to use the AIQ. And ASK, I'm going to use just white. This is the input. Okay, and the excitatory is yellow, so I can keep yellow. So, okay. That's okay. Okay, yeah, the color helps to make it a bit more clear. Better? Yeah. Correct. The retinal plane does not connect to the inhibitory, which is also true if you see the biology. The inhibitory interneurons do not receive inputs from the stimuli. Well, as far as we know, I mean, someone might discover it, we don't know. But insofar as we understand, it is going to the layer, the middle layer, right? If you know, actually inputs go here, this layer, right? From the retinal input in biology, they go here. Then it goes up, and then it goes down, and then it goes up. And then before, I think, forgot which one it was, probably deep layer, then it goes out again. Yeah. Okay? So, and that is excitatory. But the inhibitory layer, we're talking about these fellas here, right? They're part of inside there, they don't receive the input directly. Yeah. As far as we know, but someone might discover something. Yeah. Okay. It's always very careful about biology. Biology is, you don't care. You just do whatever they want to do, and then it's waiting for us to discover. So far, this is how we understand the organization. Any other questions? Yeah. Yeah. Mm-hmm. Yes. Yeah, you picked it up. So we'll talk, and it maybe make more sense in the activation function. But you realize that when you set this thing, These weights means that although our array is 169 by 169, right? WE is 169 by 169. So is WEI, WIE. They're all 169 by 169. Although the size of the array is 169 by 169, this restriction means that most of them are zeros. Okay? And in fact, you'll see the weights updating. We don't actually update these weights. I haven't even talked about the learning rule yet, right? But the learning rule only applies here, you know? Okay, you'll see. Okay, we actually don't update these weights. We fix these weights. Okay, and most of them are zeros. Yeah, so you'll see. It becomes clear when you talk about the even more qualifications. Any other questions? Okay, so do we need a break? Let's take a 5-minute break, okay? 5-minute break, and then we'll come back to the activation function and the learning rule, and then that'll be it, okay? All right, 5 minutes. Okay, let's start up again, and I'm gonna kind of drive home the point a little bit about those settings. There's some good questions just now. Hang on a minute. Oh, I'm gonna pull up the screen. Effectively, when he instantiates, second. Oh, I guess it was that one. So I think I can clear this. Okay. So effectively, when von der Mausberg was fixing the weights, let's talk about the inhibitory layer first. The inhibitory layer, what it will, if you see this, the excitatory layer will only excite because anything greater than or equals to 2 is set to 0, which means only the neighbors will excite the neighbors. So the excitatory layer will have this kind of phenomenon here. Only neighbors will, this given neuron or unit will only excite the immediate neighbors, but does not excite anything else beyond that. Okay? Then for the inhibitory layer, it will only inhibit the layers, but nothing, it will inhibit these, I think, the next layers, but not anything beyond and not itself. Okay? So that's the net effect of the settings that we described here on the bottom left here. Okay? Having these will instantiate just now that figure from von der Mausberg, that the neighbors will excite each other in the neighbors will excite each other in the excitatory layer, and the inhibitory units will only excite around the inhibitory layer, but not beyond and not in itself. It won't inhibit itself. I think it actually, no, if you excite it to 2, I forgot what the geometry is. It depends on the R here. But I think, yeah, it will inhibit exactly at the ring, but not these in this ring and not the beyond the rings. Okay? So that's how the geometry works out. Okay, because the goal for von der Mausberg, remember we go back. The idea for him was to compare the effect that, to examine the fact that, well, we already know some genetic determined thing, right? And fixing these weights means that we are fixing some genetic determinants. What is the genetic determinant of here? So think about a baby that is born, eyes closed from the womb, come out. It's never seen lines before, okay? But the baby's brain already has V1. And the V1 already has inhibitory connections and excitatory connections and retinal connections, right? Baby's brain already has this. This came from DNA. And the DNA, we said it is fixed, okay? What the baby's brain doesn't know is that in the environment, there are orientation lines. So these weights can learn, and we will see later. Okay, these weights learn because this is new. This is from the environment, not determined by the DNA. Okay, this is kind of like his instantiation of the determinant part. And the question was that if, let's say, we already have the determined part, just because of experience, can we drive self-organization in this layer? Okay? We don't want this to learn. If this learns and then we see something, well, again, we can fall back, because it can learn something, right? So then not so much self-organization, but we determined it by imposing some learning function. But let's say there's nothing to learn here. It's already been determined by genetics. And then only thing is coming in from the environmental signals. Can it still show some learning, so to speak, beyond just, because the weights are fixed? Yeah? So how come there's some pattern happening here if we already fixed the weight? So the explanation must be it can only come out from the environment. Okay? So that's why, if you find it hard to understand why these weights are fixed, That's kind of like actually establishing his point that, well, I didn't let it learn, it still showed me some pattern. So it must be coming in from the environment. And likewise, if we biologically, the baby's brain already has some set connections, and it still further reorganized itself to have cortical columns, must be because it suddenly opened its eyes and saw lines in the environment. Okay? That's the whole beauty of this setup here. All right, so where am I at? Okay, so I'm going to go on to, so this is the architecture. We're going to talk about the activation function, and things might become a little bit clearer, or maybe not, we'll see. Okay, so activation function that is used here is going to be the ReLU function. Essentially, it's ReLU, regularized linear unit, or ReLU. Okay, and it looks like this. It's very simple. This is going to be the, well, just because we already calculated, I can do this. Right? Fall back onto our standard notation, I and J, okay, input and output, where the pre-activation state of the output neuron, which is AJ prime, is equals to the summations that we all saw just now. So those, up to this point, everything was pre-activation states. So it's always about the prime. Okay? I haven't applied a nonlinear function yet. So essentially, the prime pre-activation state is going to be at some threshold theta, and then I'm going to see the actual activation state, AJ. What is it going to be? A ReLU function looks like this. Okay? And such that AJ is going to be the f of AJ prime, and it's going to be equals to the max of AJ prime minus theta 0. Yeah. It's dangerous because there's infinity, and if there's an infinity there, you can bet we're going to do some bias normalization nonsense. Okay. I hate bias. I think it's an engineering solution to the to the problem. I mean, there is biological truth to it, but the way it's implemented, just to me, it's like, what? Okay. Okay, can you see how max AJ prime minus theta versus 0 will instantiate ReLU? Yeah? Anything less than theta will be set to 0 because it will be greater than, because it will be negative, and therefore 0 is maximum. Anything greater than theta, it will take the value of the deviation from the theta. Okay? So that will be it. Okay? So that's ReLU, and that's very simple, right? You just apply this function onto these AJ primes, and that will that you calculate the actual activities that we want, which are the AEHs and the AIQs. Okay. Any questions about this? This should be pretty straightforward. So in other words, if we were to because we know what AJ prime is. Right, we just we have two activations in question, which we need sorry, this is not correct. Yep. We have to calculate these two activities to then feed it back and then to drive the activity states, right? To see how the activity will evolve of the excitatory layer. The result that we are interested in is the excitatory layer. Okay. In other words, we want to make the excitatory layer behave such that if we give it this data table input, the excitatory layer initial activity before training, the activity will look something like that. Not anything meaningful. Okay, this is the excitatory layer when I give it stimulus 1. Okay, so when I give it this stimulus 1, the excitatory layer untrained will look like this. 2, 3, 4, the 9 stimuli, it will look like this. After training, it should look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? So after training, this is what we want to see. The excitatory layer looks like that. Essentially, a different way of visualization is like this. They will have this organization. Okay? All right. It's just the same as that, just kind of implying the orientation into the visualization. That's all. Okay. So we need to calculate these activities, put it into the network architecture, and let it update its activity, okay, given the weights over a few iterations, and see if it settles in a way that will have some pattern in relation to some organized pattern in relation to the 9 inputs. Now, the other critical thing is, of course, the learning rule. So we have this. Learning or updating rule. Okay, and as I said, the only learning is done by the K, E, H's at time t. Okay, the new weights is equals to the old weights plus H. Sorry, this is not H. This is eta. Right. Learning rate. And you'll see, you will recognize this form. You recognize this form? You recognize this? No? Dot product of 2 vectors. It's an auto encode. So in other words, the learning rule is an auto encode. It's a hot field. Okay, it's not any backprop nonsense. Okay. So, which is Hebbian. So in other words, what von der Mossberg is saying is that, okay, let's fix the architecture because of genetic determinants of cells connecting. Then let's use what we know about how neurons can update themselves when they experience things, which is Hebbian. Okay, nothing computational. It's all very biological. Okay, and then let's see if we can do self-organization. That's it. All right. So this is why it's quite pretty, okay, the von der Mossberg approach here. Okay. So this is the learning rule. Of course, we do incorporate some notion of learning rates, so borrowing from, but this is not borrowing, this precedes the backprop, okay, it's 1970s, okay? But there's this notion that, okay, learning signals, the degree to which I agree with, the input agrees with my current state, that's the AA prime, you know, the product, that similarity, dot product similarity, might be adjusted, right, by some level to say if I want it to be more important than my memory or less important than my memory. So in sort of applying some momentum to. Okay, and then using that to update the weights of the input to the excitatory layer. Okay, remember we fixed the weights of the other arrays. The last bit to note in the normal, as I said before, in the operation of this in this network is this nasty normalization thing because of the infinity here. It might go out of hand. So you always, the activity cannot go out to infinity. Neurons do not do that. So every batch learning for weight updating, so we will do batch updating, we have to renormalize the weights. And what that means is that, well, after we calculate W prime, right, the weight updating amount, the actual weights to update, okay, which is now no more prime at time t, the actual weights, right, no prime, here there was prime, now no more prime, is going to be equals to the prime component, the prime value, okay, and this is nasty. Whatever this is. Okay. It's disgusting. Yeah. Dot. Let me write this properly. It means all the input units, all the excitatory units. The dot is not a acronym. It's real dot. Okay. Okay. All of the input units with respect to a given excitatory unit layer. And this S here is random number from 0 to S. Okay, and this is nasty. And this is going to be von der Mausburg himself, and I'll tell you this is the shocker here. What is S? Hang on, give me a second. S is 0.25. Okay, why? Okay, I'll tell you this next week. Okay, all right. This will go into another domain. When we see the code, it will make a little bit more sense. Okay, but it is basically a cap. You have to fix something, so you fix this, and because you fix this, the weights will always be squashed back to some range of all your existing weights by some factor. All right? Okay, you can see what this is trying to do. It's adjusting the original weights by some factor which comes from something, some constant you fixed based with respect to all the other weights, and then that's your actual weight. So this makes it such that although it's ReLU, the activity of the network is not going to go out of hand. It's going to always be modulated within some fixed range. So where the backprop, the normalization bias, went into fixing a unit by 1 and then making that as a hinge point, this one changes all the weights by squashing it within some range. Sort of what the bias unit is doing, but in kind of a different way. Because what that one was, it was a sigmoid function, and the units were always going to be maximum 1 anyway. Okay, here the units can go up to infinity. So some different way of normalization. Okay, so this is effectively the kind of the theory, the setup, and the pieces, the conceptual guts of the VDM model the architecture, activation function, learning rule, and if we implement that, there are some hyperparameters to use, which is that, so for example, some hyperparameters are this S maximum number of states, basically kind of idea, ratio, and then the distances and all these kind of things, those are some of the hyperparameters that will be set. But all these pieces put together will give you this von der Waals-Berg simulation. And the test is, at the end of the day, if I give you those 9 orientations, whether your excitatory layer, this baby here, okay, in the upper right, okay, is going to, if you let the activity evolve after learning, that whether it's going to have that nice orientation columns or it's just still going to be random relative to when you haven't trained it. Yeah. And that would be the mission. That would be the assignment. That's the setup here. Okay. Now, next week we will try to go into the code, but the first part of the coding problem is this baby here, right? How do you do that? We operate on a Cartesian grid, square. X, Y, Z is 1, 2, 3, 4, right? How to do this? Okay? You can ask ChatGPT, it'll probably give you an answer already very quickly now. I tell you, like 20 years ago when we were doing this, like this is a headache. Okay? To go from a grid system to a different coordinate system. It's a deep mathematical problem. It's two bases, two manifolds you are trying to align to each other. Okay, it's a transformation. It's a mathematical geometrical transformation and all that, right? But it's doable. Obviously, it's just some math involved. That's all. Okay. So one of the critical things is we want to implement it as von der Waals-Berg implemented it. This will be a critical step. Now, one last bit, practical question. Why do we have to use the hexagon? Why don't we just do everything in grid and then make orientation lines in grid? Yes, we can do that. You can, if you want to, okay? But then that will be deviating from the von der Waals-Berg original approach, right? Yes, there's really no practical reason why you can't just, well, if we scale things up, then everything is Cartesian grid anyway. You can still do orientation lines, and then you just scale up your model, and you can see somewhat the same thing. Yeah, sure. Okay, no one's stopping you from doing that. But if you want to try it this way, because of the beauty of the hexagon being more fair to the radius, okay? Because if you use grid, the radius 2 is not going to be the same for diagonal in squares, right? The orthogonal directions are shorter distance than the diagonals. So you run into that kind of fake problem, yeah, because if you use Cartesian. Whereas the hexagon is naturally about the radius. Okay, so that's one key reason why you might argue for sticking to the hexagon. Okay, yeah, but no practical reason for you to not use the grid if you want to. If you want to use the grid and solve these similar problems, that's fine too. Then you save time and headache about the hexagons. Okay, any questions about the background intro to VDM model today? Okay, if not, then that's it for today. I hope you are busy with your backprop. The hot field and is due, and then at the end of the month. But the assignment 2 should be due today, and then. If you are done with hot field or whatever, I've opened the backprop too. You can go and busy with the backprop, okay? And if there are any other problems in between, do raise and let me know on the NTU Cool system. Okay, thank you. That's it for today.